Hello, my name is Vladimir Choque Flores. I'm a reservoir engineer and professor at the IFE School. I am delighted to be with you during this lesson. I'm going to present the fundamentals of reservoir engineering and the basic field description of a reservoir. Many questions may arise at this point. For instance, what is the role of reservoir engineering? How and why do we characterize the fluid within the reservoir? How and why do we characterize the rock that form the reservoir? How is the fluid within the reservoir going to flow? In order to clarify our first question, let us look at the current scheme. The role of reservoir engineering throughout the life of a hydrocarbon field starts during the exploration phase, especially during the appraisal or delineation phase, in which several studies will be carried out in order to maximize hydrocarbon production. The development and the production phase will also use a lot of input from the reservoir engineering. Therefore, there is indeed a broad participation of reservoir engineers throughout the life cycle in conjunction with the other domains. It is important to mention that reservoir engineering is an integrated discipline which works in parallel with other disciplines such as geology, geophysics, drilling, and production. Therefore, a close link does or should exist between them in order to truly achieve the common objectives. We shall split our study of reservoir engineering into three parts. In the first part, we will describe the field through data interpretation in close collaboration with geoscience disciplines. In the second part, we'll look at the way in which the field behaves, production mechanisms and recoverable hydrocarbons, commonly called reserves, and finally, in the third part, we will present the reservoir simulation model and its main objectives, stating the definition of a field development strategy. Let us now focus on the field description part, which will cover fluid and rock characterization and fluid flow behavior. In order to describe the field, reservoir engineers begin by working with geoscientists in order to define the internal and external reservoir architecture, identifying unit flow and barriers. Afterward, the fluid must be characterized, defining its composition and type of fluid in reservoir conditions, answering questions such as, is it an oil? Is it a gas? A proper characterization of the behavior of the fluid will be obtained as a function of pressure and temperature. Then, we shall recall some concepts in rock characterization that are important to the dynamic behavior of the reservoir, such as porosity and permeability. We will finish with a description of fluid behavior in the reservoir, which is a function of the reservoir's pressure and the pressure in the well. All the previous aspects should help us to evaluate the original hydrocarbons in place, OHIP, which is a key value in deciding whether to continue with the studies or not, as it will give us an idea of the size of the fluids in place. Let's begin with the fluid characterization. If we consider a small section in our reservoir and zoom in, we are able to look into the porous system in detail, in terms of rock and fluids present in it. The reservoir fluids are mainly constituted of organic elements as hydrocarbons containing only carbon and hydrogen. Reservoir fluids may also contain impurities, such as nitrogen, oxygen, sulfur, and heavy metals. Some gas may also be present, containing hydrogen sulfide, H2S, and carbon dioxide, CO2. Finally, we also find water in the reservoir, better known as brine, which is essentially salty water. In order to characterize the reservoir fluid, quality-checked samples are taken in the exploration and appraisal wells. Once the fluid samples are validated with quality-check indicators, some specific tests are performed in a specialized laboratory to determine the fluid composition, the saturation pressure, and the phase diagram, which I will explain on the next slide. Properties such as viscosity, density, and specific gravity are defined as well. The phase diagram is defined through a pressure versus temperature plot. better known as the phase envelope. This envelope describes the behavior of the fluid at different reservoir pressure and temperature conditions, having a liquid phase and a vapor phase outside the envelope, and inside the envelope a mixture of liquid and vapor phases may coexist. The bubble point curve defines the bubble point pressure, PB, which is the pressure at which the first bubble of gas appears in the liquid phase. Below this pressure, higher values of vapor will be present in the fluid. The critical point is the critical pressure and temperature at which liquid and vapor coexist, and is particular to each component of the fluid. This critical point, therefore, may be used as a reference for a detailed characterization of the fluid. In an equation, for instance, the so-called equation of state. Similarly to the bubble point curve, the dew point curve defines the dew point pressure PD, which is the pressure at which the first droplet of liquid appears in the vapor phase. With this pressure, higher values of liquid will be present in the fluid. Then we must define what kind of fluid we do have in the reservoir, as this will define a classification of the hydrocarbon fluids. We do that by comparing the reservoir conditions to the phase diagram. For instance, a non-volatile oil at reservoir conditions is only oil, but once at surface, a few droplets of gas may appear and therefore be produced together with the oil. In the case of a volatile oil, the volume of gas produced at the surface is much higher than in the previous case, but the fluid at the reservoir condition is still monophasic, liquid only. In the case of a gas condensate reservoir, the presence of only gas at reservoir condition and the production of gas and oil at the surface is one of its main characteristics. It should be noted that the volume of oil at the surface may be considerable, and therefore the necessary equipment to handle these volumes must be anticipated. A wet gas reservoir has the characteristic of having gas only at the reservoir condition and a quantity of produced oil at the surface considerably less than in gas condensate reservoir. Production strategy at the surface, therefore, needs to be different. A dry gas reservoir has the characteristic of producing only gas at the surface and having also gas only at reservoir conditions. For an easier manipulations on manual calculations or else numerical simulations, the fluid in a reservoir may be treated as a black oil model. The fluid is assumed to be composed of two pseudo-components, oil and gas, having a constant composition with a constant temperature. Three pseudo-components are then defined: oil, gas, and water. As water is always present in the reservoir and therefore will be produced together with the other fluids. The oil formation volume factor VO is the relationship between the volume of oil in reservoir and in surface conditions, being Vg the gas formation volume factor using a similar relationship. The solution gas-oil ratio RS defines the quantity of gas in solution in the oil in stock tank conditions. To summarize, a smaller volume of oil compared from reservoir to surface may be produced due to the gas present in the solution of oil, and more gas may be also produced due to the expansion of gas from reservoir to surface conditions. Let us now see the main parameters in order to characterize the reservoir rock from a dynamic point of view. One of them is the porosity, and as explained previously by Jean-Pierre Deflandre, the porosity represents the amount of void in a medium, such as whole volumes in a piece of cheese. In other words, the porosity characterizes the rock's ability to store fluids and will be an important parameter in hydrocarbon accumulations and ultimately in hydrocarbon productions if these voids are in fact connected. The equation here helps us to calculate porosity if the bulk volume and the volume of grains is known. Another important rock characteristic is the permeability, and as stated earlier, it is the property that reflects the ability of a material to allow fluids to displace through it. Essentially, it represents the way pore and/or open fracture networks are connected. Permeability is reported in darcies, or more generally in millidarcies. The higher the compaction of the rock, the less its porosity and permeability will be. Since the permeability characterizes the rock's ability to let any fluid to move through the porous media, it means the pores connectivity. Therefore, if pores are not connected, the fluids contained on these unconnected pores cannot be produced. The higher the permeability, the lower the pressure differential in the porous media. This is represented in the figure by the thickness of the arrow K. Once we have described the fluid and the rock, we can now describe the behavior of the fluid flow in the porous media. This will determine the initial conditions of pressure and saturation at any point in the reservoir and the mobility of the fluids in the reservoir, and hence their replacement. In the graph, we can see that the saturation of water, SW, is related to the quantity of water present in the voids. The oil saturation, SO, is the volume of oil or in general hydrocarbon present in the voids. We can highlight that the sum of SW and SO equals to 1 or 100%. Saturation is measured in percentage and is dimensionless. There are different forces that will determine the displacement of fluids in the reservoir. The viscous forces, where the viscosity is an important parameter. The gravity forces, where the deepening of the reservoir is very important. And the capillary forces, determined by the capillary pressure and the wettability. These forces appear as a consequence of the small dimensions of the porous media. The smaller the pore radius, the stronger the capillary forces, as illustrated in the figure. In the same way, the wettability will be important in the displacement. The wettability represents the interactions between the fluid and the rock's surface. If the rock is water wet, the oil phase displacement will be easier, and the oil recovery will be higher. In contrast, if the rock is oil wet, the oil will stay encroached to the rock, and the recovery will be lower. The recovery will be explained deeper in the next lesson. As presented previously, the saturation of the fluids, oil and water, is an important definition in both displacement and the recovery in order to know the oil and water saturation in the reservoir. 3 zones are identified: the aquifer or water zone, where there is 100% of water, so the water saturation is 1. The oil leg or column, where the oil water in place is the irreducible water saturation, connect water saturation, SWC. Remember the migration in the petroleum system presented by Jean-Pierre de Flandre. The transition zone, where the water saturation evolves from 1 to connate water saturation, SWC. This evolution is estimated through the capillary pressure curve, knowing that the capillary pressure is defined as the difference between the oil and the water pressure. It is important to highlight as well that the water saturation will help us calculate the original hydrocarbons in place. In the next section, we will look at the recovery and associated production mechanisms of the reservoir.